Rsa is one of the first practicable public key cryptosystems and is widely used for secure data transmission. In such a cryptosystem, the encryption key is public and differs from the decryption key, which is kept secret. In Rsa, this asymmetry is based on the practical difficulty of factoring the product of two large prime numbers, the factoring problem. Rsa stands for Ron Rivest, Shamir and Leonard Adleman, who first publicly described the algorithm in 1977. Clifford Cox, an English mathematician, had developed an equivalent system in 1973, but it wasn't declassified until 1997. A user of Rsa creates and then publishes a public key based on the two large prime numbers, along with an auxiliary value. The prime numbers must be kept secret. Anyone can use the public key to encrypt a message, but with currently published methods, if the public key is large enough, only someone with knowledge of the prime factors can feasibly decode the message. Breaking Rsa encryption is known as the Rsa problem. It is an open question whether it is as hard as the factoring problem. History. The Rsa algorithm was publicly described in 1977 by Ron Rivest, Shamir, and Leonard Adleman at MIT. The letters Rsa are the initials of their surnames, listed in the same order as on the paper. MIT was granted U.S. Patent 4,405,829 for a cryptographic communication system and method that used the algorithm in 1983. The patent would have expired on September 21, 2000, but the algorithm was released to the public domain by Rsa Security on September 6, 2000, 2 weeks earlier. Since a paper describing the algorithm had been published in August 1977, prior to the December 1977 filing date of the patent application, regulations in much of the rest of the world precluded patents elsewhere and only the U.S. patent was granted. Had Cox's work been publicly known, a patent in the U.S. might not have been possible either. From the DWPI's abstract of the patent. The system includes a communications channel coupled to at least one terminal having an encoding device and to at least one terminal having a decoding device. A message to be transferred is enciphered to ciphertext at the encoding terminal by encoding the message as a number m in a predetermined set. That number is then raised to a first predetermined power and finally computed. The remainder or residue, C, is computed when the exponentiated number is divided by the product of two predetermined prime numbers. Clifford Cox, an English mathematician working for the UK intelligence agency GCHQ, described an equivalent system in an internal document in 1973, but given the relatively expensive computers needed to implement it at the time, it was mostly considered a curiosity and, as far as is publicly known, was never deployed. His discovery, however, was not revealed until 1998 due to its top-secret classification, and Rivest, Shamir, and Adleman devised Rsa independently of Cox's work. Operation. The Rsa algorithm involves three steps: key generation, encryption and decryption. Key generation. Rsa involves a public key and a private key. The public key can be known by everyone and is used for encrypting messages. Messages encrypted with the public key can only be decrypted in a reasonable amount of time using the private key. The keys for the Rsa algorithm are generated the following way: choose two distinct prime numbers p and q. For security purposes, the integers p and q should be chosen at random, and should be of similar bit length. Prime integers can be efficiently found using a primality test. Compute n equals pq. N is used as the modulus for both the public and private keys. Its length, usually expressed in bits, is the key length. Compute I, n, equals I, p, I, q, equals, qa1, equals n, where I is Euler's totient function. Choose an integer e such that 1, e, I, n, and gcd, e, I, n equals 1. That is, e and I, n, are coprime. E is released as the public key exponent. E having a short bit length and small Hamming weight results in more efficient encryption. Most commonly 216 plus 1 equals 65,537. However, much smaller values of E have been shown to be less secure in some settings. Determine D as dA permil A1. That is, D is the multiplicative inverse of E. This is more clearly stated as, solve for D given dar E A permil 1, this is often computed using the extended Euclidean algorithm. Using the pseudocode in the modular integers section, inputs A and N correspond to E and I, N, respectively. D is kept as the private key exponent. The public key consists of the modulus N and the public exponent E. The private key consists of the modulus N and the private exponent D, which must be kept secret. P, Q, and I, N, must also be kept secret because they can be used to calculate D. An alternative, used by PKCS number 1, is to choose D matching D a permil 1 with I equals LCM, PA1, QA1, where LCM is the least common multiple. Using I instead of I, N, allows more choices for D. I can also be defined using the Carmichael function, I, N. The ANSIX 9.31 standard prescribes, IEEE 1363 describes, and PKCS number 1 allows, that P and Q match additional requirements, being strong primes, and being different enough that format factorization fails. Encryption: Alice transmits her public key to Bob and keeps the private key secret. Bob then wishes to send message M to Alice. He first turns M into an integer M, such that 0AA permil ma AN by using an agreed-upon reversible protocol known as a padding scheme. He then computes the ciphertext C corresponding to. This can be done quickly using the method of exponentiation by squaring. Bob then transmits C to Alice. Note that at least 9 values of M will yield a ciphertext C equal to M, but this is very unlikely to occur in practice. Decryption: Alice can recover M from C by using her private key exponent D via computing. Given M, she can recover the original message M by reversing the padding scheme. In practice, there are more efficient methods of calculating CD using the pre-computed values below. A worked example: here is an example of Rsa encryption and decryption. The parameters used here are artificially small, but one can also use OpenSSL to generate and examine a real key pair. Choose 2 distinct prime numbers, such as, and. Compute n equals pq giving. Compute the totient of the product as I, n, equals, qa1, giving. Choose any number 1, e less than 3120 that is k' to 3120. Choosing a prime number for e leaves us only to check that e is not a divisor of 3120. Let. Compute d, the modular multiplicative inverse of e, yielding. The public key is. For a padded plaintext message M, the encryption function is. The private key is. For an encrypted ciphertext C, the decryption function is. For instance, in order to encrypt M equals 65, we calculate. To decrypt C equals 2790, we calculate. Both of these calculations can be computed efficiently using the square and multiply algorithm for modular exponentiation. In real-life situations the prime selected would be much larger. In our example it would be trivial to factor n, 3233 back to the primes p and q. Given e, also from the public key, we could then compute d and so acquire the private key. Practical implementations use the Chinese remainder theorem to speed up the calculation using modulus of factors. The values dp, dq and qinv, which are part of the private key, are computed as follows. Here is how dp, dq and qinv are used for efficient decryption. Signing messages: suppose Alice uses Bob's public key to send him an encrypted message. In the message, she can claim to be Alice, but Bob has no way of verifying that the message was actually from Alice, since anyone can use Bob's public key to send him encrypted messages. In order to verify the origin of a message, Rsa can also be used to sign a message. Suppose Alice wishes to send a signed message to Bob. She can use her own private key to do so. She produces a hash value of the message, raises it to the power of d, and attaches it as a signature to the message. When Bob receives the signed message, He uses the same hash algorithm in conjunction with Alice's public key. He raises the signature to the power of e, and compares the resulting hash value with the message's actual hash value. If the two agree, he knows that the author of the message was in possession of Alice's private key, and that the message has not been tampered with since. Proofs of correctness. Proof using Fermat's Little Theorem. The proof of the correctness of Rsa is based on Fermat's Little Theorem. This theorem states that if p is prime and p does not divide an integer, then we want to show THATD a permel M for every integer M when p and q are distinct prime numbers and e and d are positive integers satisfying. We can write for some non-negative integer h. To check two numbers, like med and m, are congruent mod pq, it suffices to check they are congruent mod p and mod q separately. To show med a permel M, we consider two cases, ma permel 0 and m0. In the first case med is a multiple of p, so med a permel 0 a permel M. In the second case, where we used Fermat's Little Theorem to replace mp1 mod p with 1. The verification that med a permel M proceeds in a similar way, treating separately the cases ma permel 0 and m0, using Fermat's Little Theorem for modulus q in the second case. This completes the proof that, for any integer m. Proof using Euler's theorem. Although the original paper of Rivest, Shamir, and Adleman used Fermat's Little Theorem to explain why Rsa works, it is common to find proofs that rely instead on Euler's theorem. We want to show that med a permel M, where n equals pq is a product of two different prime numbers and e and d are positive integers satisfying ed a permel 1. Since e and d are positive, we can write ed equals 1 plus high, n, for some non-negative integer h. Assuming that m is relatively prime to n, we have where the second last congruence follows from the Euler's theorem. When m is not relatively prime to n, the argument just given is invalid. This is highly improbable. Numbers have this property, but even in this case the desired congruence is still true. Either ma permel 0 or ma permel 0, and these cases can be treated using the previous proof. Padding. Attacks against Planar Sa. There are a number of attacks against Planar Sa as described below. When encrypting with low encryption exponents and small values of the m, the result of m is strictly less than the modulus n. In this case, ciphertexts can be easily decrypted by taking the eth root of the ciphertext over the integers. If the same clear text message is sent to e or more recipients in an encrypted way, and the receivers share the same exponent e, but different p, q, and therefore n, then it is easy to decrypt the original clear text message via the Chinese remainder theorem. Zhou and Hyenstad noticed that this attack is possible even if the clear texts are not equal, but the attacker knows a linear relation between them. This attack was later improved by Don Coppersmith. Because Rsa encryption is a deterministic encryption algorithm, an attacker can successfully launch a chosen plaintext attack against the cryptosystem, by encrypting likely plaintexts under the public key and test if they are equal to the ciphertext. A cryptosystem is called semantically secure if an attacker cannot distinguish two encryptions from each other even if the attacker knows the corresponding plaintexts. As described above, Rsa without padding is not semantically secure. Rsa has the property that the product of two ciphertexts is equal to the encryption of the product of the respective plaintexts. That is m1 m2 e a permel e. Because of this multiplicative property, a chosen ciphertext attack is possible. For example, an attacker, who wants to know the decryption of a ciphertext ca permel me may ask the holder of the private key to decrypt an unsuspicious-looking ciphertext car euro squared a permel k for some value chosen by the attacker. Because of the multiplicative property car euro squared is the encryption of Mr. Hence, if the attacker is successful with the attack, he will learn Mr. from which he can derive the message m by multiplying Mr. with the modular inverse of a modulo n. Padding schemes. To avoid these problems, practical Rsa implementations typically embed some form of structured, randomized padding into the value m before encrypting it. This padding ensures that m does not fall into the range of insecure plaintexts, and that a given message, once padded, will encrypt to one of a large number of different possible ciphertexts. Standards such as PKCS number 1 have been carefully designed to securely pad messages prior to RSA encryption. Because these schemes pad the plaintext M with some number of additional bits, the size of the unpadded message M must be somewhat smaller. RSA padding schemes must be carefully designed so as to prevent sophisticated attacks which may be facilitated by a predictable message structure. Early versions of the PKCS number 1 standard used a construction that appears to make Rsa semantically secure. However, at Eurocrypt 2000, Ron al. showed that for some types of messages, this padding does not provide a high enough level of security. Furthermore, at Crypto 1998, Batcher showed that this version is vulnerable to a practical adaptive chosen ciphertext attack. Later versions of the standard include optimal asymmetric encryption padding, which prevents these attacks. As such, OAP should be used in any new application, and PKCS number 1 v1.5 padding should be replaced wherever possible. The PKCS number 1 standard also incorporates processing schemes designed to provide additional security for RSA signatures. Secure padding schemes such as Rsa PSS are as essential for the security of message signing as they are for message encryption. 2 U.S. patents on PSS were granted. However, these patents expired on 24 July 2009 and 25 April 2010, respectively. Use of PSS no longer seems to be encumbered by patents. Note that using different RSA key pairs for encryption and signing is potentially more secure. Security and practical considerations. Using the Chinese remainder algorithm, for efficiency many popular crypto libraries use the following optimization for decryption and signing based on the Chinese remainder theorem. The following values are pre-computed and stored as part of the private key, and the primes from the key generation, and these values allow the recipient to compute the exponentiation m equals cd more efficiently as follows. This is more efficient than computing ma per mil cd even though two modular exponentiations have to be computed. The reason is that these two modular exponentiations both use a smaller exponent and a smaller modulus. Integer factorization and Rsa problem. The security of the Rsa cryptosystem is based on two mathematical problems, the problem of factoring large numbers and the Rsa problem. Full decryption of an Rsa ciphertext is thought to be infeasible on the assumption that both of these problems are hard, that is, no efficient algorithm exists for solving them. Providing security against partial decryption may require the addition of a secure padding scheme. The Rsa problem is defined as the task of taking ETH roots modulo a composite n, recovering a value m such that Ca per mil me, where is an Rsa public key and C is an Rsa ciphertext. Currently the most promising approach to solving the Rsa problem is to factor the modulus n. With the ability to recover prime factors, an attacker can compute the secret exponent d from a public key, then decrypt C using the standard procedure. To accomplish this, an attacker factors n into P in Q, and computes QA1, which allows the determination of D from E. No polynomial time method for factoring large integers on a classical computer has yet been found, but has not been proven that none exists. See integer factorization for a discussion of this problem. Rivest, Shamir and Adleman note that Miller has shown that assuming the extended Riemann hypothesis finding D from N and E is as hard as factoring N into P and Q. However, Rivest, Shamir and Adleman note that they have not found a proof that inverting Rsa is equally hard as factoring. As of 2010, the largest factored Rsa number was 768 bits long. Its factorization, by a state-of-the-art distributed implementation, took around 1500 CPU years. This means that, at this date, no larger Rsa key has been factored. In practice, Rsa keys are typically 1024 to 2048 bits long. Some experts believe that 1024-bit keys may become breakable in the near future. Few see any way that 4096-bit keys could be broken in the foreseeable future. Therefore, it is generally presumed that Rsa is secure if n is sufficiently large. If n is 300 bits or shorter, it can be factored in a few hours on a personal computer, using software already freely available. Keys of 512 bits have been shown to be practically breakable in 1999 when Rsa 155 was factored by using several hundred computers and are now factored in a few weeks using common hardware. Exploits using 512-bit code signing certificates that may have been factored were reported in 2011. A theoretical hardware device named Twirl and described by Shamir and Leonard in 2003 called into question the security of 10 24-bit keys. It is currently recommended that n be at least 2048 bits long. In 1994, Peter Shaw showed that a quantum computer would be able to factor in polynomial time, breaking Rsa. See Rsa's algorithm. Faulty key generation. Finding the large primes p and q is usually done by testing random numbers of the right size with probabilistic primality tests which quickly eliminate virtually all non-primes. Numbers p and q should not be too close, lest the Fermat factorization for n be successful. If PAQ, for instance, is less than 2n1/4, solving for p and q is trivial. Furthermore, if either PA1 or QA1 has only small prime factors, n can be factored quickly by Pollard's PA1 algorithm, and these values of p or q should therefore be discarded as well. It is important that the private key d be large enough. Michael J. Wiener showed that if p is between q and 2q and d, n13, then d can be computed efficiently from n and e. There is no known attack against small public exponents such as e equals 3, provided that proper padding is used. Coppersmiths Attack has many applications in attacking Rsa, specifically if the public exponent e is small and if the encrypted message is short and not padded. 65,537 is a commonly used value for Rsa. This value can be regarded as a compromise between avoiding potential small exponent attacks and still allowing efficient encryptions. The NIST special publication on computer security does not allow public exponents e smaller than 65,537, but does not state a reason for this restriction. Importance of strong random number generation. A cryptographically strong random number generator, which has been properly seeded with adequate entropy, must be used to generate the primes p and q. An analysis comparing millions of public keys gathered from the Internet was carried out in early 2012 by Arjun K. Lenstra, James P. Hughes, Maxime Augier, Jock W. Boss, Horson Kleienjung and Christoph Wichter. They were able to factor 0.2% of the keys using only Euclid's algorithm. They exploited a weakness unique to cryptosystems based on integer factorization. If n equals pq is one public key and now euro squared equals par euro squared qa euro squared is another, then if by chance p equals par euro squared, then a simple computation of GCD, n, now euro squared equals p factors both n and now euro squared, totally compromising both keys. Lenstra al. Note that this problem can be minimized by using a strong random seed of bit length twice the intended security level, or by employing a deterministic function to choose q given p, instead of choosing p and q independently. Nadia Henninger was part of a group that did a similar experiment. They used an idea of Daniel J. Bernstein to compute the GCD of each Rsa key n against the product of all the other keys now euro squared they had found, instead of computing each GCD, n, now euro squared separately, thereby achieving a very significant speed-up since after one large division the GCD problem is of normal size. Henninger says in her blog that the bad keys occurred almost entirely in embedded applications, including firewalls, routers, VPN devices, remote server administration devices, printers, projectors, and VoIP phones from over 30 manufacturers. Henninger explains that the one shared prime problem uncovered by the two groups results from situations where the pseudo-random number generator is poorly seeded initially and then reseeded between the generation of the first and second primes. Using seeds of sufficiently high entropy obtained from keystroke timings or electronic diode noise or atmospheric noise from a radio receiver tuned between stations should solve the problem. Strong random number generation is important throughout every phase of public key cryptography. For instance, If a weak generator is used for the symmetric keys that are being distributed by Rsa, then an eavesdropper could bypass the Rsa and guess the symmetric keys directly. Timing attacks. Kocher described a new attack on Rsa in 1995. If the attacker knows Alice's hardware in sufficient detail and is able to measure the decryption times for several known ciphertexts, she can deduce the decryption key quickly. This attack can also be applied against the Rsa signature scheme. In 2003, Bonney and Bromley demonstrated a more practical attack capable of recovering Rsa factorizations over a network connection-enabled web server. This attack takes advantage of information leaked by the Chinese remainder theorem optimization used by many Rsa implementations. One way to thwart these attacks is to ensure that the decryption operation takes a constant amount of time for every ciphertext. However, this approach can significantly reduce performance. Instead, most Rsa implementations use an alternate technique known as cryptographic blinding. Rsa blinding makes use of the multiplicative property of Rsa. Instead of computing CD, Alice first chooses a secret random value and computes. The result of this computation after applying Euler's theorem is RCD, and so the effect of A can be removed by multiplying by its inverse. A new value of A is chosen for each ciphertext. With blinding applied, the decryption time is no longer correlated to the value of the input ciphertext, and so the timing attack fails. Adaptive chosen ciphertext attacks. In 1998, Daniel Blankenbacher described the first practical adaptive chosen ciphertext attack against Rsa encrypted messages using the PKCS number 1v1 padding scheme. Due to flaws with the PKCS number 1 scheme, Blankenbacher was able to mount a practical attack against Rsa implementations of the secure socket layer protocol, and to recover session keys. As a result of this work, cryptographers now recommend the use of provably secure padding schemes such as optimal asymmetric encryption padding, and Rsa Laboratories has released new versions of PKCS number 1 that are not vulnerable to these attacks. Side channel analysis attacks. A side channel attack using branch prediction analysis has been described. Many processors use a branch predictor to determine whether a conditional branch in the instruction flow of a program is likely to be taken or not. Often these processors also implement simultaneous multi-threading. Branch prediction analysis attacks use a spy process to discover the private key when processed with these processors. Simple branch prediction analysis claims to improve BPA in a non-statistical way. In their paper, On the Power of Simple Branch Prediction Analysis, the authors of SBPA claim to have discovered 508 out of 512 bits of an Rsa key in 10 iterations. A power fault attack on Rsa implementations has been described in 2010. The authors recovered the key by varying the CPU power voltage outside limits. This caused multiple power faults on the server. See also, key exchange, Diffie-Hellman key exchange, key management, cryptographic key length, computational complexity theory, acoustic cryptanalysis, notes. References. Further reading, Meanses, Alfred. Van Washot, Paul C. Vanstone, Scott. A Handbook of Applied Cryptography. CRC Press. ISBN A0-8493-8523-7. Corman, Thomas H. Lesserson, Charles E. Rivest, Ronald L. Stein, Clifford. Introduction to Algorithms. MIT Press and McGraw-Hill PPA 881 €887. ISBN A0-262-03293-7. External links. The original Rsa patent is filed with the U.S. Patent Office by Rivest. Ronald L. Shamir. Oddy, Adleman. Leonard M., December 14, 1977, U.S. Patent 4405829. PKCS number 1, Rsa Cryptography Standard. The PKCS number 1 standard provides recommendations for the implementation of public key cryptography based on the Rsa algorithm, covering the following aspects: cryptographic primitives, encryption schemes, signature schemes with appendix, ASN1 syntax for representing keys and for identifying the schemes. Explanation of Rsa using colored lamps on YouTube, thorough walkthrough of Rsa, prime number hide-and-seek, how the Rsa cipher works, 1 Rsa set in Clifford Cox, Jean-Pierre Seifert, on the power of simple branch prediction analysis, a new vulnerability in Rsa cryptography, Cassette News blog, example of an Rsa implementation with PKCS number 1 padding, Koch's article about timing attacks, an animated explanation of Rsa with its mathematical background by Cryptool, a spreadsheet implementing Rsa, hacking secret ciphers with Python, Chapter 24, Public Key Cryptography and the Rsa Cipher, Grime, James. Rsa Encryption. Numberphil. Brady Hare and A.